Kia ora. Differentiation from first principles. Last year, we learnt how to differentiate using a bit of a trick or a shortcut. And now what we're going to do is to actually learn where that comes from. So let's look at this general example. The gradient of the curve at A is the limit as h tends towards 0 of the gradient of AB. So what does that mean? We'll animate this to understand. If I reduce the length of h, have a look at what's happening to the gradient of this line, AB. Hopefully you can see that what's happening is as h is tending towards 0, the gradient of that line is the same as the gradient of the curve at that point. The gradient of the line AB is rise over run. So the way we would write that down is f of x plus h, so the higher y value, minus f of x, so the lower y value, so the change in y, all divided by the change in x, which is our run, and in this case would just be the length h. The gradient of the curve at A is going to be the limit as h tends to 0 of f of x plus h minus f of x all over h. And this is how you can solve equations and differentiate them using first principles. Let's look at this example. Differentiate f of x is equal to 6x squared from first principles. So here's our formula for the derivative. Now hopefully what you're doing when you look at this is reminding yourself how to do this from last year in terms of being able to differentiate 6x squared. Maybe in your mind you're saying to yourself, oh, that's right, I multiply the 2 times 6 and then reduce the power. So we know the answer should be 12x to the power of 1, or 12x, but let's see if we can get there from using first principles. So f of x plus h, what does that mean? Have a look at what's just written here. Okay, so what I've got here is 6 x plus h all squared. So instead of writing x, we're just writing x plus h and putting it in brackets. Then we're minusing off the original function, 6x squared, and then just putting all divided by h. So that's the first step. But x plus h all squared, we can expand that to x squared plus 2xh plus h squared. So if we substitute that in, the equation would look like this. Then what we'd do is we'd just simply expand and simplify what's happening inside those brackets. So if we expand out the multiplying by 6, we would get a line like this, and then hopefully when you do this, you'd see that you're going to cancel out the 6x squareds. So what are we left with now? We should have that the gradient is the limit as h tends towards 0 of 12xh plus 6h squared all divided by h. But we can simplify again. If we didn't and we substituted in h equals 0, then we get 0 divided by 0. So we know that that isn't the right time to put in that limit. Instead, we'll look to simplify. So what we can see there is there's a common factor of h on the top line. If we pull that out, we would then be able to cancel it from the top and bottom line. So then what we'd have is simply the limit as h tends towards 0 of 12x plus 6h. At this point, we can substitute in h tends towards 0, and there we have it. Our derivative is equal to 12x, which is hopefully what we already knew. I love differentiating from first principles, and I hope you will too. So what I want you to do now is to go to page 258 in the new textbook and work on exercise 14.07, and every second question will do. All right, good luck.